Okay, so let's continue with our example. I've asked you to use a vector diagram to represent the boat's velocity in still water and the current's velocity. And that's what I've done here actually. When you have a boat traveling in still water and it's heading straight across a river, you see, going from point A and goes to point B. Let's assume this is where you have the river in between these vertical lines. And then you have the current of the river. Basically, the current we apply downwards. Okay, so the current velocity rather we face downwards because it goes down to the bottom of the river. So that's why we have from point C goes downwards to point D. The line signify, you see, this line is different from let me show you this. This line is different from this arrowed line. Okay? This line, the first one, is just a line. I'll do this. This is just a line without direction, okay? This is a line without direction. This is a vector. Vector, let me do this. Because the arrow, this, represents the direction. And also it has a magnitude, okay? If it points down, this shows the direction of that object. If it points this way, it shows the direction. And usually we would draw this poles, and this is the north. Now I'm missing my point, my poles. North, south, east, west, right? Please tell me, am I right? Is it east, west, or west, east? No, it's west, east, right? Oh, sorry, I'm missing that. It's west, east. I need to clean this. Sorry, I missed that. North, south, west, east. So it's north, south. Thank you. West, east. So you have this, your pole. And then this will help us to know the direction. You can have an object traveling northeast, but you must show with the arrow that it's traveling northeast. You can have an object traveling east-south. You see? You can have an object traveling west-south or southwest. You can have an object traveling northwest. Okay? So you see, everything has a direction. You also can have an object traveling directly to the eastward. You can have an object traveling westward. You can have another one traveling northward and southward. So this shows us we have represented our lines as vector. So that is what I mean by using a vector diagram. The vector diagram would show the magnitude of it and would also show us the direction. All right, have I answered your question? Bradley. Okay. So we basically use resultant to sum two vectors. Okay. When you have two vectors like we had here, we have vector AB, and we have another vector CD. We want to sum up these two vectors. How we sum the two vectors up is using resultant. Okay? So here we're considering the same example, and we want to find the resultant of both vectors AB. You see now, I have put that arrow AB to tell you this is not just a line, but a vector. You see? And the angle it makes with the direction it's heading. Okay, so we can actually solve this. We can find the resultant using two methods. We have either the parallelogram method or we have the triangular method. Okay, either ways you get the same answer. So let's consider the first, which is the parallelogram method. Here, we remember this same, we're considering this same example, okay? And now we want to find the resultant of these two vectors. That's what we want to do. And here, we have drawn this line. Let me signify this as north, okay? And this as south. And this maybe east, okay? And this side will be the west. All right. So in this case, we have the boat sailing eastward, and it's sailing at 12 miles per hour. Okay. Then we have the current of the sea. The current velocity is 4 miles per hour. And it's sailing, remember, downward, so it's southward. And this is, I mean, the current is downward, which is southward, and the boat is sailing eastward, which is A to this point. All right. Now we want to find the resultant between these two vectors. All we just do is we draw this resultant line, which also has a direction. Okay. Then how do we find R? That is now going to be using parallelogram method. Remember that this side, let me start with A, let me say AE, is parallel. I don't want to mess up that line. This is what I mean by parallel. AE is parallel to this dotted line. Do you agree? Do you agree? Okay. And then AS, let's say AS is this, is also going to have a parallel line. So it's parallel to this side. Okay? Since we have this side AS parallel to this and AE parallel to this, we can easily then find the resultant between the two lines. How? That's because AS, which is 4, this side will also be 4. Of course, they are parallel. This is 12 AE, this will also be 12, right? And this is what? What is this value of this angle? Can someone tell me? What is this? What is, let me call this alpha. What is alpha? Okay, thank you. Alpha is equal to theta. Okay, so we already have 4, 12, theta, right? And then we simply use our Pythagoras theorem to find R. And R is what? Because this is angle 90, remember? Then R will be 12 square plus 4 square, and you take the square root of it. Why are we taking the square root? Because r squared equal to 12 squared plus 4 squared. Okay, and to find r, you just do the square root of everything. So r, the resultant, will give us 13 miles per hour. We also asked to find the angle it makes with the direction it's heading. So this theta now is what we're looking for, theta or alpha, whichever one. Okay, and to find theta, it's heading this direction, right? It's heading east, eastward. Let's say it's east-south or southeast, whichever one you call it. So we're going to have tan theta. That's opposite of our adjacent, right? The opposite of this is 4, and the adjacent side of it is 12. Okay. Someone is asking, how did I get 30 miles? Okay, let's do the, please do your calculation. 12 squared is 144 plus 16. Take the square root of it. Have you found it? Kinanele. Kinanele, it's 12.65, right? Did you get to, okay, thanks. And then you approximate it to 13. All right, that's fine, we can proceed. Okay, and then when you want to find the angle it makes, it's just going to be tan theta, which will be equal to your opposite side, 4, divided by your adjacent. The adjacent is 12, right? And when you do arctan of 4/12, you're going to have, you're going to have 18 degrees. Are we all on the same page? Can we proceed to the next slide? Yes, KD, you round up 12.65, which will be equal to 13 degrees. Not degrees, 13 miles per hour. Talenta, round up 12.65. What is it going to be? No, we are looking at miles per hour. It's not degrees. That's the distance. You can only convert, yes, 18.4, round it up, it's going to be 18. If that is in miles, if you have got 12.65 degrees, then you can start changing it to minutes and to seconds. There's a question that I've missed. Okay. I think I'll just take this example again. There's a lot of question coming from it. I try not to go over this again because of our time. Yeah, so your colleague has answered. It's because of the vector diagram we had before. Okay, so yeah, let's proceed. So that if you have any other question, you can also raise it at the end of the class, please. All right. So this is the triangle method, which you can also consider working it out yourself. It's just that, like I've explained to you, this is the initial one that we drew, and we can represent it this way, whereby angle theta, angle of depression, is the same thing as angle of elevation. And that's all we have done here using triangle method. Okay. This is another example where we have considered air navigation. This is an air navigation example. We have a jet flying at 240 miles per hour, and it's heading, okay, at 60 degrees. Just follow the example. When you have a jet which is taking off, it goes up. It doesn't go up vertically. It goes up at an angle. And that's what this means, heading. So on a heading, and I've said it's the direction in which the jet is pointing, of 60 degree, when the wind is 30 miles per hour from 33 degrees. Remember that wind now is the opposing force, okay? And it's going to be pulling it down, like trying to reduce the speed of the plane. So we have been told to draw the air navigation diagram to compute the ground speed, that is the jet speed with respect to the ground. And that will be the resultant. Take note, the ground speed will be the resultant speed. And then find the drift angle, that is the wind correction angle, and determine the cause. All of these terms, I've underlined them so that and I've given the meaning to each, so that you will know what and how to indicate it in your diagram. We'll see the diagram, you see how I've indicated it, and then determine the cause, that is the direction of jet's movement with respect to the ground. Let me take it just quickly to the diagram. Then you can ask your questions from this diagram. I'll explain using this diagram how the jet flies. It picks up from origin 0, right? Remember, we usually draw a pole, north, east, south, and then west. So you have your jet starting from origin 0, and it takes off eastward. I've drawn it eastward because that's the positive side, actually. When it goes to the west, then you'll be talking about negative side. But in most cases, we start from the positive. That's the first quadrant, like you have learned. So we start from origin. The jet starts from origin and flies up and makes this angle 60 heading. It goes, and explain why this angle is 60. It's not the angle to the ground, it's the angle to this North Pole. And why is that the case? When the jet keeps going, it can still make a heading upward and upward. By the time it makes a heading at angle 90 degrees, then you have the jet flying horizontal vertically. But because the jet is not expected to do that, then it makes an angle towards to the North Pole. That's what we call the heading. Those in aeronautic will understand this, but that's actually how we calculate the angle, the heading angle. It makes an angle to the North Pole. Okay, and that's what we call the heading. Then there's a drift angle. That drift angle, let me go back to this, you see what it means, is the wind correction angle, because the wind would want it to come back. Now you see it here. The wind we still have to draw our North Pole. The wind would pull it down. We want it to go down and pull it also back. So there's a wind correction angle, which is the drift angle. No. Yes, is the drift angle. That's correct, which is this theta. I hope we can all see it, please. The picture is, the diagram is tiny, but yeah, there's this tiny angle. I don't want to mess it up. Let me do it here. This angle, theta. Can you all see that? Okay, so that's the drift angle that the wind makes. But remember, the wind's angle itself is 360 degrees. I'll take you back again. It says when the jet is pointing 60 degrees, when the wind is 30 miles per hour from 330 degrees. From this. And that is why we have, it goes westward. It travels, okay. It goes from the North Pole, here. Let me draw it again here to see it better. So you have the wind going that way, making this angle like this. While you may want to think it should go this way, right? But can someone tell me why it's going clockwise? I've drawn two directions here. One is anti-clockwise, and we know normally when we want to compute our angles, we must compute it anti-clockwise. We go from 1, 2 quadrants, 3 quadrants, and 4 quadrants. But can someone tell me why the wind's angle goes clockwise? Does anyone know why the wind's angle goes clockwise? Yes. I just want to be sure everyone is following. Thank you. It's to oppose the motion. It's the opposing force. Yes. Okay. Thank you. I'm happy we are all following. And then we have been told to compute the ground speed. Remember, the ground speed will be the resultant force. It's this, or the resultant speed. Now we're not working with force, it's the speed. So the resultant, because this wind will pull it, we want to pull downward, okay? And then, so we're going to have, let me clear this and draw another one. So we're going to have this kind of triangle. Remember, with directions. This is the speed direction. With directions, this is the jet direction, and this will be the resultant. This is O, origin. Okay? And here, this angle is theta, which is what? The drift angle. We don't know what the drift angle is. We only know this side, 240, right? We have this side, 30 degrees, 30 miles per hour, and we are told to find R, this side. Okay, so the ground speed is very straightforward to compute. And what are we using? We're using the Pythagoras theorem here. This is the resultant, this one. So we have used Pythagoras to compute this. Okay, 240 square plus 30 square, and you take the square root of it, and you find your ground speed, which is your resultant speed. Is that fine? Do we agree to that? This is what you're asking. Talenta. Okay. So let's find the drift angle, which is theta, this angle theta. To find angle theta, we have opposite and we have hypotenuse, adjacent rather. This is theta. Remember this drift angle, the small one, this theta I've drawn here. And this is 90 degrees. So this is opposite and this is hypotenuse. And this is, I keep saying hypotenuse. This is 30 is opposite, 240 is adjacent, R is hypotenuse. So what trig ratio are we using? We're using tan, and that is how we got this. Okay, please be sure, do your computation and see that we have the same answer, please. I don't, Black Hope, I don't understand the question. How do you get theta in degrees? Basically, you use a North Pole as a reference. Basically, that's normal. That's by default. Black Hope, I'm trying to understand your question. How do you get theta in degrees? It's just arctan. Am I not getting the question, Black Hope? I need to understand what you're asking. Okay. And to get the cos, which is this addition of heading plus drift angle. Okay. That's the addition of heading. That's this addition of heading plus drift angle. All right. So yeah, that's how you find the cos. And you can see from the diagram, the cos, it's just heading and drift. And it's just 60 plus theta. And 60 plus theta is 67.1 degrees. I will find now. What's the use of the wind angle? How will it affect the ground speed if it was 300 degrees? Let me take the first question, which is from Milos. The wind angle has actually been given when you do 360 minus 330, okay, that will give you 30 degrees, right? And what we have indicated here shows that this is actually an acute angle. So if you make it 300, if the airspeed is now 300, then it's not always 60. This is just an example. It's an example where we have used the heading to be 60. The heading can be 30 degrees, while the wind angle can be 300. In that case, we assume 90 degrees. If the angle it makes is not 60, if the heading angle is not 60, let's say it's 50, and let's say the wind angle is 300, then we would not have this as a will not have this to be 90 degrees, and then we'll not be able to solve it using this approach, using the Pythagoras theorem. We can calculate, do 360 minus 330. That's 30 degrees, right? That will give you 30 degrees. And you have this heading angle is 60, which forms 90 degree. If you go back, let me just do this. I want everyone to understand, because questions like this may come out in your test. Let me take you back. This is what we have done. So we have said this is an acute angle. So depending on the angle that is given, if the angle given is not 60 degrees, then you don't say it's 60 degrees. Yeah, gone past that. You say, so far, final answer, of course, do we just give the angle, or do we need to add direction to the answer? Yeah, it's not asking you to in what direction, actually. So that's why we have given it an angle. In degrees, just in degrees. If I ask in what direction, then you need to provide the direction, north, south, northeast, southwest, and all of that. Okay. Let me also pause the recording.